Mhm. Oke, suaraku jelas?
We are channeling the company's artificial intelligence efforts into one recognizable organization, Qualcomm AI Research. Qualcomm invents breakthrough technology that transforms the way the world connects and communicates. Going beyond mobile chipsets, we're inventing AI technology that can be used across a wide range of products and industries, from mobile and automotive to smart homes and cities, ultimately changing the way people live for the better.
Machine learning has already entered every corner of the Qualcomm enterprise. I personally believe that Qualcomm is uniquely positioned to become a key player in on-device AI, which brings with it tremendous opportunities such as increased data privacy for users, reliability of service, high speed and efficient use of bandwidth.
Today, machine learning algorithms such as deep learning use huge amounts of energy to power them. And as AI increasingly moves to low-power edge devices, energy efficiency becomes all the more important.
The challenge we face in the future is about squeezing as much as computation as possible out of every joule of energy. And Qualcomm has a long history of delivering technologies that do just that.
Our mission is to push the envelope of AI and machine learning in the areas that will significantly improve everyday life. We are asking challenging questions, like how do we preserve communication privacy? Can we use deep learning to compress videos? How can we eliminate uncertainty when making life and death decisions? And how can we use this knowledge to optimize Qualcomm chips that run machine learning algorithms?
Qualcomm AI Research is an inspiring environment where researchers collaborate, innovate, and share their findings with the world through high-impact publications. But we do so much more than just writing papers. We actually build AI solutions that are used in billions of devices. In your cell phone, your smartwatch, your drone, your car, and all the other innovative technology of the future.
So if you're interested in pushing the frontiers of artificial intelligence, machine learning or deep learning, and above all, if you feel passionate about the prospect of bringing ideas to life and impacting billions of people, then Qualcomm AI Research is the place for you.
Semua hal berangkat dari sebuah awal. Begitupun kami menjadi pionir. Memutar roda penggerak bangsa dan terus melaju. Kami hadir seperti sebuah keluarga. Dan terus fokus membangun perekonomian negeri. Menjadi yang terdepan, mewujudkan mimpi-mimpi besar. Dari atas awan kami terus bergerak dan berinovasi, melihat negeri ini tumbuh dan berkembang. Inilah kami yang tak akan pernah berhenti, mengantarkan Indonesia ke puncak kejayaan. Karena dimanapun dan kapanpun, kami selalu hadir melayani dengan setulus hati.
History, most of the time, is born out of the simplest of acts, just like the birth of our story, starting with the pursuit to close the distance through voice and make exchange.
Okay, it's 4 p.m. in here. Thank you, Daniel, for joining us again for the third lecture of the second day. And you can expect to have more and more questions yeah, from the participants. They are really interested in your speech, and I think today is no different. Yeah, for that, I think you can just start your talk, so we have more time for questions.
Perfect. Yes, and thanks, Pak Said. I am very happy to receive questions on this material or on the material from the past 2 days if people have outstanding questions that need answering. Okay, let me just share my screen. Right. Here we are. Just okay. Right, so today I'm going to be talking about a topic which I've been working on personally in my own research for the last few years. Oh, so I think you need to turn your microphone off. Sorry. Thank you. And in my front, still, if you ever make it to Bali, these 3 girls are performing what's called a legong dance. It's a really, really beautiful dance, usually performed by young girls. And this image in particular is taken from one of my favorite movies, which is called Samsara. And the opening scene is yeah, pretty incredible. So equivariance is an area of active research. So unlike the previous 2 lectures, this is really about sort of fresh ideas which have only been around maybe 4 or 5 years at most. And some of these works are actually new in the last few months. So this is really cutting edge research you're going to find out about today. And I'm going to cover the following topics. I don't really need to tell you, but I'm going to say it anyway, that CNNs, convolutional neural networks, which Vincent just gave you a tutorial on, are responsible for many successes. So considering, say, the ImageNet competition, and I've got a sort of an image here, a graph here of years from 2011 to 2016, and you can see the error rate in the competition going from, I think it's about 30-something% down to 2.7% in 5 years. We are so successful on the ImageNet competition that we no longer even hold it in its original form. That's how well convolutional neural networks have performed. Convolutional neural networks aren't just for things like classification, though. They've been used for things like semantic segmentation, as you see here. This is a topic where you have an image on the left and you have to label every pixel into one of, I think in this case, 17 or 19 classes. And the ground truth is on the right. So basically the different colors represent different classes, car, human, tree, or whatever. And this is something called a dilated residual network in the middle, and this is what it's predicting. We can do actually a lot better than dilated residual networks now. This is just, this was the first time, for me at least, that I started really paying attention to this literature. CNNs can also be used for something completely different from image data. This is an example of something called a wavenet, where it's a version of a convolutional neural network called a causal convolutional dilated network is used to do speech synthesis. And so you have an autoregressive problem. That means it's a problem which sort of eats in its input and it produces, its output becomes its input at the next sort of iteration of running. And this is an example where they were able to do speech synthesis, and it was a paper from DeepMind. Whoops. I think Aaron von den Oors was on this paper. And if you go on their website, you can listen to some of the speech and music samples generated by this network, and they are extremely good. Really, really amazing stuff. So what is it that these three different areas have in common? Well, it's convolutions. It might be that we use different specific architectures in each of these problems, but we use convolutions for all of them. And convolutions are a building block that you've been introduced to in the last 2 days. And it's an area, well, it's basically what I research. So what exactly is a convolution? And to understand that, we need to understand inductive biases and this problem of overfitting that I talked about yesterday. So here I have an example, and I think I showed it yesterday, where I have a couple of data points. There's 10 data points, and they're generated from a cubic polynomial with a bit of extra Gaussian noise added. So that's a third order polynomial in red. It's the same one across all of these stills. And then what I'm doing is I'm fitting curves of increasing order to these data points. So linear, quadratic, cubic, quartic, quintic, etc. And you can see as I increase the order between all of these images that I can fit these data points better and better and better. But as I said yesterday, you're going to generalize to new data points less and less well. But obviously, if you have too low an order, you can't fit the points in the first place. So you have underfitting on one side, and you have overfitting on the other. And it's a bit like if you know the story of Goldilocks, you just want to find something in the middle which is just right. And this is sort of encapsulated in this sort of schematic, or this sort of diagram here, where each box sort of represents a space of functions, a space of all the functions you could possibly have. And the true function will be in here somewhere. And we're just trying to find a space of functions which is not too large. If it's too large, then you end up fitting all of these spurious sort of correlations here and you overfit. If it's too small, you can't actually model the true underlying function. You want to find the function space, so here f2, which is just big enough to include our true function, but not too big that either it takes a really long time to find the true function through things like optimization, or where we end up fitting artifacts in the data. And so this is about removing extra degrees of freedom that do not aid generalization. This is the aim of the game. We want to find the most expressive network which contains everything we need, but nothing more. Another example, okay, again with polynomial fitting. So now I've generated, so say I give you some data and I know that I generated it from a fifth order polynomial, a quintic, and it's got a bit of noise. But I don't tell you what the order is. How would you practically go about trying to figure out what polynomial to fit to this data? So this is an example of my data. It's generated in blue, and I've got some red points, which are the actual 100 generated data points. And you can see there's a bit of noise. Maybe you can't see if your screen's a bit small, but there's a little bit of noise on this as well. So maybe you might go for a maximum a posteriori approach. You've got a likelihood, you put a prior, which encourages your weights of your polynomial to be small. You get a posterior out and you take the maximum of the posterior. I'm not saying that this is a good technique, but it is just one of the techniques you could use. So if you plot something like the negative log likelihood using the map estimate here, or if you use, say, the negative evidence, it's this term on the bottom. Remember, this is the two different ways you could measure how well your model is doing, or how well it predicts your data set. And if you plot that against polynomial order on the bottom, so here I try a flat line, a linear line, a quadratic, cubic, etc. When I increase my model complexity, these negative log likelihoods get better. So down is better because we're looking at negative log likelihood. Obviously, if it was just log likelihood, up would be better. And so you see in this region here, we have a very, very large negative log likelihood. That's not very good. And why is it large? It's because we're not fitting our data very well. But then over here, it seems like we can fit our test data, our training data perfectly. And that's what the blue line shows. And the red line is very, very close to it. Essentially, it's sort of averaging over different possible explanations, but it's very close. But the optimal polynomial order we know is 5, because that's what the true polynomial order is. So it's, I mean, if you actually look closely enough, this is actually the minimum of this curve, and this sort of slopes up slightly, but it is very, very hard to see that, especially from this example here. Note the logarithmic axis, but it is very, very hard to see that. So maybe I might try something else. Maybe you give me multiple versions of this data set and I can do the bias variance decomposition. And if I do that, I can plot my variance, I can plot my bias against polynomial order measured in whatever units are necessary. And if you do that, what we're actually interested is the bias squared plus the variance, because that's equal to our total error, as I said yesterday. And that's the purple line. You might not be able to see it. It hugs the bias here, then it goes down and it comes up. And you see for sure the minimum of this is this point here at the 5th order polynomial. And well, we already know that our model is too rigid over here, but over here, what happens on the right-hand side is that this goes up because we now have too much variance. What does variance mean again? It means that our model is fitting to spurious correlations in the training data. But the problem is, as I said yesterday, we can't actually plot the bias variance decomposition in reality, because we don't have access to multiple versions of the training data, unless you do something special like bootstrapping or something like that. So the question is, how do we find this point here if we actually don't have access to these values on the right-hand side? Again, this is the idea. We want to find the smallest function space possible which models the data. Well, the idea is just, well, why don't we just try and find this, use the least complex or the simplest model we can which fits the data. And this sort of falls into this area of inductive biases. Inductive biases is about adding extra structure into a model, as much structure as you possibly can, but where you still fit the data very well. An extra structure will always increase bias. But maybe we can increase bias to a point where it doesn't actually negatively impact our modeling. So here I have a spectrum from white to black. And on one side of the modeling spectrum, you have these things called white box models. This is what scientists have been doing for the last 400 or so years, or even longer. This is about scientists creating models which are very, very detailed about the world. You know, they've got these models of quantum physics, of Newtonian physics, relativistic physics, of chemistry, electron orbital, all this kind of interesting stuff, which I don't know very much about. But people have written down very detailed laws of how the universe works. And this is in white box models. On the other end of the spectrum, another modeling modality is called black box models. This is essentially models which are, they make very few assumptions about the world, and they're very data driven and data hungry. And I've got a little child here. Children are sort of sometimes thought of as black box models in the way how they learn, because they are very, very flexible. These models are not rigid at all. They're very flexible, but they take a lot of data. In reality, though, where we sit as machine learners is somewhere in the middle. And we work on these things called gray box models. This is a term from statistics, actually. And most machine learning models sit here. Regression, classification, deep learning are all versions of gray box models where we actually do have some structure. It might be, we've chosen to use polynomials, for instance, or we've chosen to use a convolutional neural network rather than a recurrent neural network. And this is because we have some knowledge about the structure of the underlying problem we're interested in solving. Is the first sort of mathematically principled way for designing neural networks. And I think it's a very exciting area. So let's recap on convolutions. You probably know them because we talked about them a lot already. A convolution is essentially, we have a convolution here instead of a linear matrix multiply. And this is the mathematical form. It's a sum between a feature map or a signal and translated copies of a filter. And if I were to write this out, you can actually reshape this into a matrix multiply, where you have a big matrix here, and your signal, you can vectorize it. And what you see is that this matrix representing this weight here has a very special band diagonal structure. And essentially, it's got two aspects. One, we have zeros in the side parts here, which reflects the locality of the signals, of the filters. So the filters here, it's only a 3x3 filter. It doesn't span the entire image. That's why you have this locality. And there's also this diagonal weight tying. So each of these, when you go down from level to level, row to row, within this matrix, you see that we have the same filter moved down and shifted across one, corresponding to a different shift of this filter here. And so this extra structure is really the locality and the weight tying. But why is it that we use locality and weight tying? What is it in the real world that says that we can use these properties? Well, it turns out the translational weight tying comes from a property of classification, and actually a lot of tasks that we do, which is translational invariance. In these two images, trivially, we have a dog, but the dog is at a different separation, a different displacement from the left-hand edge of these two images. So this task is translation invariant. Where does the locality come from? Well, it actually comes from the locality of pixel statistics. So up here, you'll see an image, and you've got an arrow. And if you look at the normalized correlation between the pixel values in a natural image, and then you average this over an entire population of images as a function of separation, as pixels get further and further apart, you actually find this really nice sort of correlation here, where pixels further apart from each other are less correlated. And that should make some sort of intuitive sense if you think about it. Pixels close together are probably part of the same object. Pixels far apart probably are not. And so because of this sort of concentration of energy on the left-hand side of this, or around the center, the zero in this graph, that's why we can use smaller filters. And so this is great because this means we have very few filters, very few parameters. So if this matrix were n by n, we'd need n squared learnable parameters. But here you see we've just got 1, 2, 3. We have a constant number of parameters. So you've reduced a quadratic a problem down to a constant cost problem in terms of number of parameters. So that's a huge reduction in the number of parameters you need, which means it's statistically efficient. You need less data as long as you are able to fit the data in the first place. And it's obviously computationally efficient. In some sense, computationally efficient, I should say. If you can do parallelization on the GPU, it's not always the case. And the reason why we use convolutions is because why should we bother to, I mean, we could have just used a linear layer here, and with enough data, technically we could just learn a convolution. It would just emerge if we have enough data. But we don't. And the reason is because we already know that this structure is useful. Lots of people have shown it's useful. Why bother learning, say, this translational weight tying structure from data when we could just build it into the network? And so the question of equivariance is about, okay, so we've done translational weight tying, and it's all about the weight tying. What about rotations, scaling, warp, shears, color jitter, blur? Can we come up with generalizations of convolutions which generalize to these other kinds of invariances? And there's an entire work, an entire literature, and I've just sort of shown a few of them here, but the normal convolution is called a translational convolution. This is what you'll have heard of, but there's a whole load of other things, and these are all less than 5 years old in the literature. And I'm going to talk about some of these different things today. And I'll come back to this diagram again and again and again. But before that, we need to understand what invariance is. So a function f, so a mapping, a layer is invariant if it satisfies this equation. So you have a function, it takes in an image I, and then if it's equal to itself, when you use a different version of the image, a transformed version of the image as the input, then it's invariant. And this T is called a transformation operator. It can stand for many different things. So it takes in an image and it spits out a new image. And then you can index it at a place, and then it will give you a, let's say a pixel value, for instance. So this would be a translation operator. This would be a version of the operator used for rotations. This would be a version used for data whitening. So this one here has no parameters because data whitening is parameterless. Just depends on the data. And symmetry is a property of the task. So symmetry is another word for invariance, essentially. So this is a property of a function. And so classification is invariant to, say, in this case, rotation and translation. Signal detection can be, so if you're searching for particles in a particle collider, that's invariant to rotations. In, oops, okay, this should move. But in dynamical systems, you might have a flip symmetry around the center of this cart pole experiment. And in the disentangling problem, in the cocktail party problem, if you don't know what it is, essentially you have multiple people speaking in a room and you have all of their speech signals overlapping. And what you want to do is you want to separate each person speaking into a separate speaker channel. And that problem is invariant to speaker identity. If I have this man as my first speaker and this woman as my second speaker, well, she could also be the first speaker and he could be the second speaker. It's invariant to permutations of the ordering of the speakers. This is a super classic machine learning problem, by the way. So this is invariance. Convolutions are not invariant, though. What they are is something called equivariance. So equivariant is a very strange term. And it corresponds to functions which satisfy this property. So essentially, a function, if I have a transformation of my input and I pass it through my function, that's the same as taking my image, passing it through the function, and then translating it in the output space. And this is best represented here. So if I have an image of, say, this retriever here, and I take features of it, were I to first transform the retriever and then take features of it, what this equation says here is that I could have taken this northern branch and closed this diagram here. So either I can get to this point by taking my features and transforming in feature space, or I can transform in the original space and then take the features, and I end up at the exact same point. And this is called a commutative diagram. So equivariant feature maps have this particular property, and convolutions actually have this property as well. And you can see this is actually a generalization of invariance, because if this operator here is the identity, so basically if this just wasn't here at all, that's just invariance. And convolutions actually have this property. So if I take my input image and I shift it, then my feature maps all shift as well. So they satisfy this property. And there's a theorem in a couple of papers which says that this thing called a group convolution, which I'll introduce in a bit, is the only linear map equivariant to things called group structured transformations. And I'll explain what that means in a minute. But essentially, this is going to be the handle which allows us to unlock the capabilities of convolution to other kinds of transformation. Just a bit more intuition about equivariance before we jump into all of these convolutional variants. This is a very strange property to have, and you might ask, why do we want this property? And there is just one extra step you need to visualize to understand why we would want this property. Say I have a second dog. So this is a pug dog here now. And when I was making these slides, actually, I realized that I probably shouldn't use dogs. I should use cats because dogs are haram. But I couldn't find good pictures of cats. I apologize to Muslims in the audience. But if I have this second dog here, and I take features, and I end up at this point here in space, and it just happens to be the exact same point as the retriever, then the features, or these two dogs are said to belong to the same equivalence class or invariance class. This feature is just a dog feature. It's not a pug or a retriever feature, it's a dog feature. Now, the interesting thing is, what happens when I rotate the dog and I then put it into feature space? Well, because we have an equivariant transformation, going down the southern branch and then going up into feature space is the same as going along the northern branch and then transforming, which means we should end up at this point here. So this is actually really interesting. Why? Because these two dogs were in the same equivalence class or invariance class beforehand, and after the transformation in image space, they're still in the same equivalence class because these two rotated dogs still map to the same point. So this is a very sophisticated version of invariance, actually. Equivariant maps, they do what we say, they preserve equivalence classes. And this is the real reason why equivariance is important, because if these two dogs were in the same equivalence class before a transformation, but they were no longer in the same equivalence class after a transformation, this would mean things like when I rotate my head, it's no longer a head. Or when I translate a car, it's no longer a car. That doesn't make sense. So this is about coherence, essentially. This is a fundamental property that we want. Okay, so you can do some maths and you can show that the convolution is equivariant in a very nice way, and you can look at this in your spare time. But let's just try and understand before we go on to the group convolution, what kind of transformations we can model. But before we do that, we have to understand this thing called a group. So, and this is, I think this is the majority of the maths in this talk. So if you can bear through this, then you can bear through the rest of it. So group theory is an abstract mathematical theory. Physicists use it a lot, chemists use it a lot, and it's used for modeling transformations. So a group is essentially a set G with elements, say little g and little h, and you can combine the elements using what's called a composition operator. And these are great for modeling transformations. So each of these elements might be a transformation. So for instance, I have this picture of an owl here, and then one of these elements, which I can apply to the image, will be a rotation. So you can label your transformation with an element h, and this would correspond to a 90-degree rotation of the owl. And what this rule says, is that if I compose transformations, so I've applied th and then I've applied tg to this, that the composition of these two operations, one applied after the other, corresponds to a new transformation. So transforming by h and then g is the same as transforming by this new element g blob h. And this blob is very, I say blob, but this composition operator is very, very abstract. It can mean many different things. It can mean multiplication, addition, matrix multiplication. It's very complicated, or very general, I should say. Here it's just addition. 90 degrees plus 135 is 225. So transformations of transformations are transformations. Then there's a property of associativity. This means that I can put brackets around my transformations in any way I want. That means I can compose in an order independent way. So I can contract these two operations into one, or these two, and it doesn't matter. I still end up with the same result. There's an identity transformation. So that means that there's a do nothing transformation. And there's an inversion. So if I rotate my owl, I can always unrotate it. And so any set of operations which correspond to, which have these four properties is called a group. That's what I should say. Any group of set of operations which have these four properties is a group. Okay, that's the mathematics. What does this mean for us? Oh, I thought I had a slide here. Sorry. Well, I'm going to tell you what it means for us. It means that there are a lot of transformations out there: flips, translations, rotations, scalings, roto-translations, which all fit into this framework. I think my slide's probably a bit further down. Sorry about that. But we can actually, we're going to build a convolution based on groups, and translation is just a special case. And then we can actually use that to generalize. So this was the original convolution. The group convolution, or the regular representation, or the left regular representation group convolution, it's got a complicated name, is this. So essentially what we've done is, beforehand we had a collection of inner products between a signal and translated versions of a filter. Now the group convolution is a generalization where we have, again, a collection of inner products between a signal, and now we're using transformed versions of a filter. So now we've replaced this translation here with a general transformation here, and we have a negative in here. It just means all the maths works out. So here, this operator can, beforehand it was just translation. If I stick in this operator here, I end up with this, but it could be a rotation. It could be rotation plus translation. This gets more general. So this is a general transformation here. And by the way, this only works with groups. So if you have a set of transformations without inversion, for instance, then this wouldn't work. And an interesting thing is, now if you think about X, it actually turns out to be the index of the transformation operator here, which is very, very interesting. So it parameterizes the output, and there's also a slightly adjusted domain, but that's just a detail. And if you look at this, if you now were to look at this in terms of what we were doing before, where we had that sort of band structured transformation here, what it says in the case of this roto-translation case is we're actually going to have blocks of transformation, and each of these might correspond to different transformed versions of our filter. This is maybe not so easy to visualize on the first pass, but essentially what you say is, I'm going to take lots of different transformations of my filter, and then each row of this matrix is going to correspond to a different transform version. So if it were just translation, then yeah, obviously this filter would just be banded along the diagonal here. Here I've done something more complicated. I've sort of taken a 3x3 permutation of this filter here, and then I've done a 3x3 permutation and also shifting along. So this would correspond to, say, rotating and translating filter. And now let's look at some examples of what this really means. I've got some visuals here. Oh, okay, so this is the slide I was looking for. So these are examples of different kinds of transformation. I think I got my slide ordering a bit wrong. But so this is a translation, rotations, roto-translations, reflections, scalings. These are all examples of group structure transformations. So if I can transform my filter in these ways, then I can build a convolution over them. A non-example of a group transformation is an occlusion. So when this bird walks behind the book, we cannot, this is not a group transformation because we cannot invert this transformation. We can't pull the bird back and retrieve this because the head's been chopped off. That information doesn't exist in this 2D projection. Okay. Okay, and now the slides I wanted to show you with the group examples. So essentially this group convolution is a very general thing. And what you have to do is you have to stick in specific examples of a specific group in here to build a specific kind of group convolution. So one is called an SO2 convolution. SO2 is just a very fancy name for rotations, 2D rotations. It actually stands for special orthogonal group of 2 dimensions. And in this form, we parameterize our transformation operator with 2x2 rotation matrices. So this just means rotate my filter. And so the output is going to be parameterized by this. But rotation matrices, actually, they sit on a circle. They sort of loop back into each other. And so they got an interesting topology. And so here what I see, and it depends on how good your internet connection is, but if you have a good one, then you will actually see this image here will have a Gaussian or kind of an elongated filter which is both rising through space and rotating. And what I'm doing is, if you go up in this space, this is showing you different rotated versions of this filter. I'm kind of taking different cross sections. And what I'm doing is I'm taking the inner product between this filter and this underlying patch, which is actually a patch from an eye image. It's a vessel. And when you take the inner product, when this filter aligns with this big black line here, you should get a blob here. So if you see this, then hopefully your resolution and your internet connection are good enough. And so this is a diagram of what's happening when I am taking inner products between the underlying F here and rotated versions of this filter. And you get essentially a line up here with two blobs corresponding to the points where the response are maximal because this is aligned with the underlying bit. Okay, so this is what the activations will look like from an SO2 convolution. It's just a one-dimensional convolution. Interestingly, one-dimensional, because it's got 1 degree of freedom, which is theta here. So what happens when I start rotating my input? Well, now I'm not going to show you this rising cross-sectional plane. Instead, I'm going to show you rotating the input, and I'm going to show you what the activations look like. Well, what happens is that you see these blobs, they start moving up through the space. And this is, you're witnessing equivariance, the equivariance property here. When I rotate my input, F, that corresponds to a translation of the activations up through the feature space. And when it comes off the top here, it pops off and it rejoins at the bottom because of the circular nature of the activation space. So this actually should be a circle, but because of the way how computer graphics work, I can't actually make it into a circle. That would be difficult to visualize. So yeah, this is an equivariant convolution, and this is a rotationally equivariant convolution. So this is a very, I hope this makes a bit of sense. This is equivalent to that image before, where you have a translating input image and you have translating features. Here we have rotating input image, and these are rotating features in the feature space, but with a more complicated geometry. Okay, so that's just a rotating convolution. A slightly more complicated version is if we look at the special Euclidean group of 2 dimensions, which is a roto-translation. So what we do here is we stick in a more complicated transformation, which has 2 parameters now. It's got rotation and translation. So you have, essentially, you can rotate an object around the center, and you can also translate where your center is. And if you stick that in, you get something which looks like this. This will just rotate and translate your filter. So before, we had just a single filter which was rotating and translating, and this gave us a single activation in the center. But now we're doing this where we don't just have a single filter rotating here, we have filters rotating at every single point in this plane. So we have a filter here, here, like every single pixel has a filter centered on it, corresponding to different translations X. And as you go up, there's also different orientations. So this is actually a 3-dimensional activation space, because we have these 2 translations, so in your X1 and X2, and a theta or an R theta direction going vertically. And this is actually, I wonder what geometry this is. I think this is a cylinder of some kind. Essentially, when you go off the top here, you should pop back onto the bottom. You should go round, so it's got a sort of a circular geometry here, but also sort of like sort of 2D in the other 2 dimensions. It's kind of difficult to explain. But anyway, you see you get this very interesting pattern here. Again, I'm using this Gaussian thing, which is why you get maximal activations at this point here, at these orientations and these orientations. What happens when I start rotating my input? Well, we can imagine these points here are going to start rising up through the space and then popping up on the bottom again. But also, because these points are going to rotate, well, you might as well just see it here. Because they rotate, the entire image is going to rotate at the same time. So this is a very complicated thing. We actually have what looks like a corkscrew motion. If I follow a single pixel through space, if I follow, say, this end here, what it does is it goes in a circular rotation and it rises through the activation space and then it pops on the bottom again. So equivariance in this case corresponds to rotations of the input correspond to corkscrew motions through the activation space. So this is a very complicated version of that translation, which I talked about earlier, but now it's rotating and translating. And these convolutions aren't just theoretical objects, they are actually used. So a new assistant professor at the Universiteit van Amsterdam, Eric Beckers, has applied this to a bunch of different things. So mitosis detection, so this is discovering mitotic cells. These are sort of cancerous cells, I believe, in histopathology images. He's used it for vessel segmentation. So you've got a fundus image of the back of the eye here, and he wants to do a segmentation to label what is a vessel, what is not a vessel, and into cell boundary segmentation here. And what he's essentially done is he's done all of these tasks, and what he's done is he's discretized the number of rotations we use in the roto-translation group. So he's built these convolutions, but he's rotated the filters as well as doing the translation as well. And along the bottom here, you have n equals 1 rotation. So this is the standard convolution. This one, standard translation, this one, this one. But he also introduces rotated versions of the filters with increasing numbers of rotations along the x-axis. And you see we get better and better performance. This is a bit weird how it goes down at the end. We have some theories for why this is, but we're not quite sure. And he's compared this with just using vanilla CNNs with data augmentation, and data augmentation does seem to help a bit, but it seems actually, in some cases, having this special group convolution works better than having a standard convolution with data augmentation. So data augmentation isn't enough. Using these things is super useful. And he also shows that you've got these error bars here. The error bars, apart from in this case, they tend to reduce in size. So you actually get sort of more confident or more robust performance with increasing numbers of rotations in your roto-translational convolution, which is a really nice result. And this basically, why do we get this behavior? Essentially, we don't have to learn to be equivariant to rotations and translations. This is built into the network. As I said before, this means you need less data, essentially. So this is great. Another example, work by Elise van der Pol, and actually me, a few months ago, we were looking into applying this to reinforcement learning. And here you have an example of a cart pole experiment. You have an inverted, I think it's a pendulum, inverted pendulum here. And the idea is to move this actuator along a rail to make sure that the pole doesn't fall off. It doesn't sort of fall down. And what we could assume is that this has a symmetry around the vertical axis, in that if I'm falling to the right, then I will apply some kind of policy to try and move this, this actuator along the rail to stop it from falling. Well, that would probably be the mirrored version compared to if I was falling along the left. So this has a symmetry. And lo and behold, yes, adding symmetry constraints into policy networks actually leads to better performance, or learning with fewer samples, I should say. So here we have training a policy network with time steps along the bottom, and we're these blue curves here. And you see you get much faster convergence on things like a grid world with a 4-way symmetry, or Pong, which has actually a vertical symmetry. So you flip around the x-axis, so top becomes bottom in here, left becomes right, and then you can have 4-way rotations. So these things are much more sample efficient. So these things aren't just for classification, they can be used in other domains as well. And I think this would be a good point for, let's say, a 5-minute break.
Sure. Yeah, let's take 5 minutes.
Yeah. If people have questions in the meantime.
Oh, you want to take some questions?
Well, I mean, if people have any questions at the moment, I'd be happy to answer for 5 minutes.
Sure. Okay, there are some questions actually. From Ebuka Oguchi. Why do you think the human visual system can recognize images with different transformation? Meanwhile, a deep neural network needs to be fed lots and lots of transformed data to do better. Yet the human brain wasn't trained on any data.
Okay, so this is a really interesting question. Thank you for that one. So it's actually, the answer is actually a bit more complicated than humans can do it and machines can't. So when it comes to things like translations and small rotations, humans actually have in their eyes, if you study the neuroscience of how the retina works and all the visual processing system works, they have these things called simple cells and complex cells, and then it goes higher, V1, V2, V4, the lateral geniculate nucleus, whatever, if you ever did computational neuroscience. And essentially, complex cells have built-in rotation invariance, I believe, built into them. And so maybe it's a process of evolution. We have developed very strong inductive biases to transformation robustness or invariance, some cases equivariance, just through the process of evolution. I'm not a neuroscientist. I only took a couple of modules back in my master's, so I remember that much. But I do know this. Babies actually, they don't have luminance invariance in the first, I think it's 4 or 6 months of being born. So if a baby is being held by a parent in daylight and it's below the age of 4 months, and it looks at the parent, and then if you change the lighting setting, so you make the light a lot darker and it looks at the parent, it doesn't recognize that that parent is the same as in the bright light. And it takes about 4 to 6 months for it to learn to see that dark objects and bright objects are the same things. And so usually, but obviously babies do know that it's the parent, then they use other cues like smell and touch and sound and stuff like that. But so there's a mixture of stuff which is learned and stuff which is hard coded into us through evolution. So that's a really interesting one, actually. So it's a big motivation for this kind of work. And it's a fantastic example of a gray box model. Oh, and why can't networks do it? Well, they can't, and that's why we're building these different kinds of convolution.
Convolutions, yeah. We manually add more and more structures.
Yes.
Okay, next questions from Cheng Wawan Chenggoro. It seems that the approaches for injecting invariance other than translation is not popular for real application. Do you have any intuition why?
Yeah, I think until now, the literature has been very difficult to read. It requires a lot of mathematics to understand. And this is a pet peeve of mine. And I'm working with my colleagues to try and make the literature a lot easier to understand, essentially. That's one reason. The other is, I don't think anyone's written a PyTorch module for this stuff yet. I think it's, as soon as someone releases a PyTorch Roto-translation or convolution module, then it will become super popular. There is actually some work by 2 researchers, Maurice Weiler and Gabriele Cesa, who have released a library to do E2 convolutions. So that's convolutions over rotation, translation, and flips. And I would highly advise using that, but still it is very, is not so simple to understand the terminology. So I'm looking maybe one of my next projects to just make a more user-friendly version. But this stuff should be used, I think.
Yeah. Right now, I think it's much easier to just use augmentation.
Yeah, it is. It's super simple. But if you could just have a module from PyTorch, that would be great. One more question, and then we start again.
Okay, one more question.
Yes.
Yeah, from Robbie Hardy Winata, the purpose of equivariance want to show that in the process of data augmentation, even though the object underwent transformation, but still in the same object handled by grouping, so that the machine will learn more dynamically, right? So it's just like a confirmation.
Oh, yes, I think. I think, yes, you've understood it. Okay, cool.
Okay,
That's
cool.
a nice short answer as well. So that's perfect. Okay, so what I just showed you was something, we have these things called group convolutions here, and I've got an entire hierarchy of different kinds of convolutions. And a special case of the group convolution is something called a unitary convolution, which I'm not going to talk about today. And a special case of the unitary convolution is the regular representation convolution. Regular representation just means when you take your filter and you transform it a bunch of times. And so a special case of the regular representation convolution were these convolutions I just showed you. So the translation one, roto-translation. So that we've just been exploring this at the moment, but it's a special case of the group convolution. Next, I'm going to talk about steerable convolutions, which are, this is how I personally got into this entire area of literature. I invented something called a harmonic network. Yeah, if you go on my Google Scholar page, I think it's my most cited paper, so it's easy to find. And what I didn't know at the time is that this is a special case of something called a steerable convolution, which Taco Cohen, who is kind of seen as the guy who sort of pushed this entire field into being, he wrote a paper on that, and I designed a special case of that. So what is a steerable convolution? Actually, we'll just stay here. Essentially, at the moment, these filters, these convolutions we built are designed where we take discrete transformations of our filters and we just make lots and lots of copies of those filters. And what I was interested in designing was something where a lot of transformations are inherently continuous. So can we have an equivariant transformation or a convolution which is equivariant to continuous transformations, to 360-degree smooth rotations? We don't have to discretize our filters. And to that, I looked at this thing called the Fourier shift theorem. So if you don't know, a Fourier transform is a transform of some signal f. So you have this curly f means Fourier of a signal f. And what it does is it breaks a signal down into individual frequencies. So if you study signal processing, or if you're a physicist, you'll be very intimate with these. And what they do is they take an inner product of f against a bunch of basis functions called, I don't know what they're called actually, complex sinusoids. And in the top half here, it looks like it's a sinusoid, but it's a complex signal. And you have this iota here is the square root of -1. Some people use I. I was an electrical engineer, so I use J. People get very angry if you choose one, so I use an I without a dot to stay neutral in this debate. And then these sinusoids are given a frequency m. I think there might need to be a 2 pi. Oh no, there doesn't have to be because it's in the limits here. But then we have different frequencies m. So if you take the inner product of one of these basis functions against a shifted version of f, and f lives on the circle, by the way, a shifted version of f, we can rewrite that by doing a change of variables to this. So I've changed from phi minus theta to phi dash, and then you get an extra theta out the end here. This change of limits, actually, because you're integrating on a circle, is the same as before. But then we just get this extra term of e to the minus iota m theta out the front. So what you end up is you actually have the Fourier transform, the original Fourier transform in the new coordinate system, plus an extra, what we call a phase shift or a phase factor out the front. So a translation here becomes an extra rotation or multiplication by this complex phase factor out the front. So this is another version of an equivariant transformation. But beforehand, I said that the group convolution was the only kind of equivariant linear transform. This is also a linear transform. It turns out convolutions and Fourier transforms are pretty much the same object under the hood, but they're equivalent up to a basis transformation, interestingly. But essentially what you can do, so this is just the statement of equivariance if you want to see it in mathematics. I lied when I said there was no more mathematics, sorry about that. But essentially what happens is if I take this image here of this letter K, and then I take the inner product, I do the Fourier transform at a single frequency with a filter here, which I'm going to call W. I'm going to relabel this as W, or W sub M, I should say. Then I will get a complex number. A complex number has a real and an imaginary component. This is represented by this phasor here. Now, if I transform, so say I rotate my image here, that's the same as doing this here. This is a rotation. Yeah, I've got radius and theta, so angle coordinates here. Now I take the inner product. What happens is that this phasor rotates by an amount m times theta. And this is represented down here. So this is an equivariance diagram. This is essentially the diagram I had with dogs before, where I have my dog, rotate the dog, feature transform, rotate the feature transform. This is the equivariance or commutative diagram as before. So what you can do is you can build a neural network with filters which are of this form. So they have an e to the iota m phi term. I've got rid of the minus because it's not so necessary. And this is a constraint on the angular form of the filters. But then you can add a couple of extra learnable things, like a learnable radius to the filter, because this is just a function of the angle. But in the radial direction, you can have any function you want. And there's a beta here, which is also, these are extra degrees of freedom you can add to the filters to give more expressivity. But they basically have this sort of harmonic sinusoidal form. I should have put some images in here. Go read the paper Harmonic Networks if you want to understand this, and if this stuff interests you. But essentially, if we look at it in terms of our diagram of doing a convolution before, essentially what you can do is you can replace your filters with various sinusoidal harmonics. And it turns out if you use for your filters these various harmonics, then you can get exact equivariance to any transformation, any smooth transformation or continuous transformation on the circle, and generalizations to general groups exist. This was just for rotations, but for general groups this exists. And it turns out that these basis functions here for general groups are called these things irreducible representations. Very complicated stuff. I always get confused by them, even though I work with them most days. But essentially, this gives you perfect equivariance. It turns out in practice that these are not so good for images because these filters are too basic. We've just constrained them to have, we've constrained their angular form too much. But if you look to the three-dimensional generalization of this work for point cloud problems, so ones where you're modeling, say, molecular graphs, if I have a molecule and it's in some configuration, if I rotate the molecule, it's exactly the same molecule, but at a different rotation. It turns out when you're trying to do things like predict the melting temperature or some other property of these models, the state-of-the-art models they're based on this precise sort of theory here, but generalized to the three-dimensional case. But the mathematics for that is it's quite difficult, I've got to say. But so this is one version of another version of a convolution called a steerable convolution. But yeah, I normally don't talk about these because these are very, very tough to talk about. They're quite complicated. So if you didn't get this, don't worry. Again, as I said yesterday, actually, this is more about exposure than anything. But these are super cool. And we actually built a network out of these. And this is an image from the BSD. So the Berkeley Segmentation Dataset 500, a little Inuit boy, I believe. And if you look at, say, the fifth layer, I think this is the fifth layer of VGG. If we rotate this image and you look at the features, so this is what the feature map looks like within the VGG. And then I've cut out a square here. And then I've rectified the image. And you look at the features, then it's got this interesting transformation here. And so there is no known equivariance in this image, interestingly. I mean, maybe equivariance has been learned, but we don't know how to extract it from this image. So when we built a network from using our technique, we did the same thing. We can actually pull out an invariant. So we get an equivariant transformation, but it turns out that we can make an invariant one super simply, and you get this performance here now, which is a lot, well, I would say a lot better, but obviously it's my own work, so I'm biased, and you can see them next to each other. So you've got the VGG stuff here, and then you've got our stuff here. So this is not perfect because of essentially sampling artifacts, but it's doing a bit better, I would say. And this work is now, yeah, doing pretty well, I'd say, on at least molecular tasks. So that was what's called a steerable convolution. Another version, something which I worked on personally in AmLab, is called a semigroup correlation. For those of you who don't know the difference between cross-correlation and convolution, we talk about convolution a lot, but technically the real name of this thing is called a cross-correlation, the way how we implement these things. The fact that we call it a convolution is actually a misnomer. It's been misnamed as a convolution. I think it comes from the original work by Jan LeCun. He should have called it a cross-correlation. But I bet cross-correlational neural networks doesn't sound as catchy as convolutional. Anyway, so this is a generalization of the group convolution. And I'm going to sort of lead into this by talking about an example of a transformation which is not group structured. So if you have a picture of an owl here and you want to rescale it, so you want to make it smaller, there is a naive way to do this and there is a correct way to do this. So the naive way to do this is, if you want to resize the image, you take every second pixel in the rows and every second pixel in the columns, and you get this image here, this subsampled image. But people who do signal processing will tell you the clever thing to do is to first band limit your image, essentially smooth it out, spread the information in the image, and then subsample. And as you increase the subsampling, you can actually see the artifacts in the naive subsampling versus the band limited subsampling. Essentially, I would say this image looks better than this one here because we have removed high frequency details in the image before subsampling, which cannot be supported by the coarse resolution of the image. Hopefully the resolution on your computer screens and your internet connection should be good enough to see this. Otherwise, just look at the lecture notes. This is 4. Okay, cool. Actually, I think this is supposed to be a ×8 here. Sorry. But rescaling is not invertible. And the reason for that is when we do a rescaling, first of all, we band limit it by some, we'll have a blurring kernel, which depends on how much we want to resize. So I've resized this by a factor of an 8th. First of all, I blur the image, and then I subsample it. And essentially, these two operations are non-invertible because I have, I don't know, I have many pixels here, and I have 1 divided by 64 of the pixels here. 64 because I'm subsampling in 2 dimensions, an 8 times 8, essentially. So I can't go from a low resolution to a high resolution image. Mathematically, you would write that as first I blur my image, and then I take every 1 on S, so every 8th pixel. I blur and I take every 8th pixel. We cannot undo this transformation. The inverse doesn't exist. It's a many-to-one problem, so inversion is 1 to many. Multiple inverses do exist, but they might not all be correct. Let's go back to group theory. What does this mean? It means we don't have an inverse. Technically, we don't have an identity. That's more of a nitpicky observation. But the thing we're left with, a set of transformations which, when I rescale a rescaled image, I could have just rescaled the original image by a bigger downsampling factor. And associativity, these two properties, if you check, they do hold for rescaling. And if you have a set of transformations which only observe these two properties, it's called a semigroup. It's called a semigroup. And so we designed something called the semigroup correlation. This is our original group convolution from Tucker Cohen and Max Welling. there's a generalization of this where we have to basically, the problem is we have this inverse here and we need to get rid of it. And there's two steps you go through. One is you pull the inverse out of the inside and you move it onto the W. That's more of a detail which we don't really have to bother with so much. But essentially what's going on here is this is a pixel-wise reindexing. This is just a transformation on the pixel positions. This allows you to include blurs into the transformation. That's the intuition. And then for a non-invertible transformation, you actually move this inverse transformation away from W and onto the image signal here. So you see it's a very simple change, and you might be thinking, so what? This is quite simple. Essentially, it's a collection of inner products between transformed versions of your input signal and a fixed kernel now. So instead of transforming the kernel or the filter, we're transforming the image. And I was pretty struck when I first saw this, because it is so stupidly simple. And I was thinking to myself, it can't be this simple. I can't publish a paper on this. But it turns out that this version of a convolution has properties which generalize this, and it's quite interesting. It's actually very complicated. It's deceivingly simple. But yeah, this is a generalization where you can have things like scalings and technically even things like occlusions, and it is equivariant to those transformations. And I use a star here instead of an asterisk. So let's see how this works in practice for, say, the first layer of a scale equivariant network. So in this case, you have your filter matrix. So maybe here I've got translated versions of a filter or something like that. But here I feed in multiple versions of my image, multiple transformed versions of my image. And you see this should be red, green, blue, and this would be downscaled versions of it. And you get multiple outputs as well, one for each transformation or transformed version of the image. So if I specialize the correlation to the thing called the scale translation group, you get this beast over here. What's going on? This is a blur. So essentially, you've taken your image and you blur it with some kernel. This might be a discrete Gaussian or some other kind of blurring kernel. In the scikit image package, there's a bunch of these things. It just gets rid of the high frequencies. And so you will blur corresponding to some downsampling factor k, or 2 to the k here. And so this, diagrammatically, if I have my image, and first of all I blur, in the group theory terminology, or sorry, in the group equivariance, or the semi-group equivariant terminology, we call this a lift. So we take multiple blurred versions of our image, one for each k. So no blur, blur of 1, 2, 3. And then what's going on here? Well, we have, if you know this form here, it's what's called a dilated convolution. So the inner product between this object, this is one object, and the filter is a dilated convolution. You can rewrite it as that. So what's happening is I'm taking translated versions of this blurred image, taking the inner product between that and W, but I have this extra factor here, which means when I increase Y by 1, I will move 1 pixel over in my filter, but I will move 2 to the K pixels over in my image. And you can actually rewrite that by, I hope you can see this, the pixels in this image getting, in the filter lying on top of the image, getting further and further apart. So what you see is you have multiple scaled, multiple blurred versions of this image with a filter that explodes larger and larger the higher up you get. And then you take the inner product between this filter and the image at different translations, and you get different feature maps with increasing levels of blur. So you see, this is very fine detail, this is very blurry. And this was really nice because in the computer vision literature going back to the 1957 actually, there's this idea of something called a scale space, a very classical object called a scale space, which is used in image processing a lot. And this was literally this collection of blurred images. And this thing here, which is derived quantity, is called a deep scale space. And we could build the equivariance images again, where I take transformations of this image. I could, if I translate it, these translate. If I scale it, there's a very complicated transformation which happens to do with these images actually moving. They downscale in size, but they also move up and down in this feature space. But I'm not going to show that in this talk, because there's other things I want to show you in the next 5 to 10 minutes before I finish. But I was very excited about this because that's a generalization of the group convolutional work. I normally make the joke that when I first came to Amsterdam, Taco said to me, "Oh, you know, your harmonic networks is a special case of my steerable convolution." So I was working a very long time to make something where his group convolution was a special case of my work. No, Taco's great actually, but we have some sort of friendly rivalry going on. But no, Taco's outdone me again, and he has a much more general work of group convolutions called the gauge equivariant convolution. A lot of people are very excited about this, and this is taking a very different approach towards convolution. So essentially, we're usually talking about, we want to build a convolution which is equivariant, or a transform which is equivariant to, say, some transformation of our input. Another way is to think of these things called local gauge transformations. And this is a very orthogonal way of thinking about the whole problem. So say I have some space here and I have a vector v in this space. A frame is another name for a coordinate system, essentially. Now, there's not necessarily a natural choice of frame. I could have this frame here, or I could choose a rotated version. I can have any coordinate system I want, or not any, but like there are many, and an infinite choice of coordinate systems I want in which I could represent this vector. And the question is, and two questions, is there a natural choice of coordinate system? Well, the answer is usually no. So two, how do we have a representation of V which is independent of the coordinate system? Well, the answer is you basically use all of the coordinate systems at once. So we represent V in this coordinate system and every rotated version of it. And so if you have a filter represented in each coordinate system rotated about some point, then you end up getting rotations of a filter. And it looks exactly like the group convolution, but it's motivated in a very, very different way. And by the way, this stuff is getting very complicated now. So if you're not following, just sit back and enjoy and don't think too hard. So it's like a group convolution, but we can define this thing locally. So it can work on manifolds, these very, very complicated surfaces. And what do I mean by that? Say you have a mesh. And so there's work by a guy called Pim de Haan, and I think it's in my references at the end, where you have a mesh which might be like a kind of a three-dimensional mesh on top of a person, for instance, or some sort of 3D shape. We can't define transformations on the mesh of a signal sitting on the mesh, but we can think of a point on the mesh, and locally everything looks kind of flat if we look locally enough. And in that flat surface, we can define a frame. And it's actually called a tangent space. And in that tangent space, we can actually perform a convolution. We can perform an inner product between all of these rotated versions of a kernel, like this, all the rotated versions, and the signal from the manifold projected into the tangent space using something called a logarithmic map, actually. And if you do that, you get the generalization of the group convolution onto very complicated surfaces where symmetry transformations may not actually exist. And there's an extra step where essentially you take every tangent space on the manifold and you project signals on the manifold into these tangent spaces. And so if I represent that here, essentially what they've done is they've taken the group convolution from before, but at every single point, they have now an extra correction matrix called a parallel transporter in the theory, which projects signals on this surface into the local coordinate systems. Here we have one coordinate, one frame, one tangent space, but we have one of these spaces sitting on every node and every vertex of this mesh. So that corresponds to each one of these blocks here. We have a different set here. So this allows us to think about group symmetries, but at a point rather than globally. These gauge convolutions are super exciting from a theoretical standpoint. But yeah, if you're interested in this, I've got a couple of slides at the end. But again, as I said, this stuff is getting quite confusing now. Even for me, some of this literature is very difficult to read, and I've been working in it for 5 years. But okay, this is just my my roundup slide, which I want to show you. Essentially, we started off with this regular representation convolution, which is just showed here. And I've shown you a couple of other examples. So I showed you, well, generalization of this to roto-translations. And then I showed you the steerable convolution, which uses a different set of filters, which are constrained to be these pure harmonics to give us continuous transformation equivariance. I showed you an example where you have non-invertible transformations and you can still get equivariance. This is the semi-group correlation over here, which is one potential generalization of a group convolution. And I just showed you the gauge equivariant convolution, which is where we define group convolutions, but not on an entire surface, but individually at multiple points on a surface, because it may not be that I can actually transform a signal on an arbitrary surface around very easily. So this is looking at local transformations versus global ones. And this is a separate generalization of the group convolution. So technically you could merge semi-group correlations with gauge convolutions. So you'd get, I don't know, semi-group gauge correlations or something like that. And this is really sort of the main sort of contenders in the world of equivariance at the moment. And these things actually do have their uses in practical terms. Just to round up, today I talked about convolutions. They're a very powerful inductive bias. And essentially they're just replacements for linear layers where we add extra symmetry constraints into the linear layers because we just want to add more structure. So it's this gray box modeling procedure. It works very well because you reduce the number of parameters by adding these extra physical, you might say, constraints. And there are many different variants. And as a result, these are very good for small amounts of data. As I showed you with the work by Elisa van der Pol with the reinforcement learning and Eric Beckers with the roto-translation stuff. If you are interested, I have, this is probably not an exhaustive list, but I've got 3 slides of related work, and I'm always looking to expand this work in the future. Okay, thank you very much. Oh, I can't hear you. Said.
Thank you very much, Daniel. I try to not think too hard, but I can't.
Okay, don't worry. The last part, I left it to the very end because it's very confusing.
I know it's a very interesting talk. Yeah, even though, yeah, like you said, it's much more mathematical compared to your previous 2 talks. But still, we have some questions for you.
Yes, yes.
Okay. Okay, from William. While most spatial transformer network utilize non-equivariant convolution, is it better to use equivariant transformer network?
Yes, so there is work by a guy called David Romero, who is actually here at the Vrije Universiteit, that's the Free University of Amsterdam, who has been doing work on equivariant transformer networks. So I would look into, I wonder if I have his, yeah, here we are. Oh wait, yes, Romero et al. Attentive group equivariant convolutional networks. and actually I've got some work on stuff similar to this, but you can combine the two, and I think it makes sense to. I think transformer networks make a lot of sense when you don't necessarily have symmetries. So language models make a lot of sense. There's no symmetries in language necessarily when you have a sentence. So transformers are great there. It seems that they work very well on images, but combining them with convolutions makes them seem to perform better. Although I think there's a trade-off between, in that case, between number of parameters and efficiency, which transformers are amazing at, and having extra constraints built in, which convolutions do.
Okay, thank you. Yeah, I think you and other researchers try to overcome the rotation invariance, right? By introducing a structure, but still it introduces a new problem. That's some people ask in the chat. How can you differentiate between 6 and 9?
I get this one so often. It's amazing how many times people say this. Sixes do not look like nines rotated. There's a rotated MNIST data set, and sixes, I don't know if I can draw it, but like a 6, I've got a piece of paper here. If you draw a 6 has got a very, very sort of curly tail, but a 9 is usually a lot straighter. I don't know if you can, oh, you can't see my...
Yeah, I can see.
Yeah,
oh,
the 6 usually has a sort of more of a curve, and the 9 is more straight. But I don't know. Like, it seems that it works in practice, but I think, yeah, maybe that's a case where you shouldn't have equivariance. So again, these inductive biases are it depends on the problem, really.
Yeah.
So you just need to model the problem. Well, I think.
Yeah, I think so. If we have like ambiguous data, so maybe we need more context, right?
Yes, absolutely.
Yeah. Okay. More questions from. Wait. Okay, from Ali Akbar. How would you relate this rotating plus translation in group convolution to self-supervised learning ideas in computer vision?
Yeah, I have to say, I'm very impressed by the questions I'm getting in the last 2 days. There's been some really, really good ones. So how do you relate this to ideas of self-supervised learning in computer vision? So I think there's a lot of interesting work going on in the unsupervised representation learning literature. So if you know these papers like SimClear, or these, what's it called? CPC, and all of these other sort of noise contrastive estimation tasks. Essentially, what they're doing is they're building unsupervised representations of data. And it seems a lot of the time that data augmentation is really important in the design of these representations. So what you do is you take an image, you take a transformed version of the image, pass them both through an encoder, and then you have a classifier in that space which says, are these two images from the same class, or are they from a different class? Because you have lots of what's called negative examples. And this builds very, very good unsupervised representations for downstream tasks later on, but it's heavily dependent on the amount of data augmentation and the kind of data augmentation you use. So I have a theory which I had with a master's student, which is that this works because precisely of the data augmentation coupled with the NCE loss, and he was able to show to some degree that that is actually the case. But they actually have a loss essentially which is encouraging equivariant, or specifically in the case invariant representations, whereas we're building it directly in. My personal belief is that at some point we're going to walk away from this sort of work, which I've been working on now, and we'll go to learning convolutions in the future, or learning them, because this stuff is horrendously complicated and you can't expect everyone to want to build these. Just learn it from examples. I hope that was a good enough answer.
I think so.
I can't give all of my ideas away for the next few years, otherwise I won't have anything to publish.
Okay. Next questions from John Middleton. The videos of SO2 equivariance and SE2 equivariance were really cool. Have you thought about equivariance to other non-compact groups, such as conformal groups?
Oh, interesting. So the problem with non-compact groups, so for those who don't know what a non-compact group is, a non-compact group is a group which has an infinite domain. So scaling is a non-compact group. This means if I take an image, I can keep on downscaling it forever. I can sort of halve its dimensions and this goes on forever. Its parameter space is infinite. Circular, so SO2 is a compact group. When I rotate my image and I keep on rotating, at some point I end up back at the start. So this space is finite in some way. So the problem with non-compact groups is that you end up, and this was actually the same with the semi-group correlation where we had scaling, is that we can't work with infinite domains in general. So you end up with a boundary. So what that means is that we have a scale space, and at some point we have to just cut it off. We just say all of the scaling is beyond this point we don't care about. And boundaries introduce boundary effects. Even actually standard translational convolutions are a non-compact group. So we've been using non-compact translational convolutions all this time. But if you ever look at the features at the boundary of an activation layer, weird stuff happens because of the padding effects. And the padding leads to, boundary effects. And knowing exactly what to do at boundaries is not obvious. Anyone who's worked in semantic segmentation will know how important padding is, and dealing with your boundaries is there. Some people say you should use a different kind of convolutional kernel at the boundaries to deal with them specifically. Others, there's people don't really know how to deal with that at the moment. It's obvious what happens on the internal sides in the bulk inside your feature space, but on the boundaries it's the tough part essentially, because you artificially have to truncate. I think you could either move to a local notion of equivariance, like in the gauge convolution, where you say symmetries no longer exist for us. We only consider symmetries at points, local symmetries, global symmetries don't exist. Or dealing with boundaries explicitly in your space in some other way. But yes, this is another great question I unfortunately have no answers for at the moment. It keeps me in a job though, it keeps me researching.
Okay, thank you, Daniel. We still have more questions from Javier. Javier is interested in security of machine learning. As you know, that deep learning, deep neural networks have issues to adversarial examples. Do you think that this group convolution can help to mitigate that problem compared to the standard convolution?
Yeah, so I'm not so well read in the adversarial literature, but I have seen 1 or 2 papers where they have tried adversarial attacks on group convolutional neural networks, and they have shown that they are more robust to certain kinds of adversarial attack, specifically ones where specific transformations which you're equivariant to are included. So essentially, I think it means that the space of adversarial attacks gets smaller when you use group convolutional neural networks. But yeah, it's not fully robust, but you have a smaller possible set of adversarial perturbations you can try.
Okay, still more questions. Okay, about the inductive bias. The topic, your lecture is advanced topics in equivariance and inductive bias.
Oh,
which part is inductive biases?
Sorry about that. I think I I changed the title to Equivariance.
Yeah.
But yeah, sorry about that. It's my fault. I should have updated the title. Well, the thing is, equivariance in itself is an inductive bias. So really, I started off by talking about inductive biases, and then I've honed in on a specific kind, which is the equivariance constraint, because it is a linear constraint we're applying to networks. In general, I think there are other kinds of inductive bias you can apply by considering the structure of problems much more deeply. I think this is an area with a lot of potential for the future, especially in the AI for science realm, where you might want to do things like have neural networks which are, say, energy preserving or something like that. Or if you're working with PDEs, you want volume preserving neural networks. But yeah, my apologies for that. It's not so specific about inductive biases. It's more about equivariance.
Okay, maybe next year, if we still have summer school, you can talk more about inductive bias.
I'd love to.
Okay, maybe one last question. Is it okay?
Sure. Yeah, no,
Okay.
you keep them coming.
Okay. From Haryanti, can we combine group convolution with separable convolution?
With separable convolutions?
Separable convolution.
Yes, you can. So, so a separable convolution is essentially if you write out this matrix here. I'm just wondering about the best way to explain it. Essentially, it means that your matrix can be written as an outer product of lower rank matrices, I think is what it is. So the standard example is if I have a 2D filter, I can write it as two 1D filters. So say convolution with a Gaussian 2D filter, I first convolve with 1D Gaussians along the rows and then 1D Gaussians along the columns. So that makes it very efficient. There has been some work by Vincent Le Petit, which showed that you can actually approximate most filters very, very well with linear combinations of separable filters. So I think that means that you can approximate most group convolutions well with separable filters. I think that would actually be a very interesting research project, because one of the problems with group convolutions is that every extra degree of transformation, degree of freedom that I introduce, so we just got the 2 for translation, then we have an extra 1 for rotation, maybe an extra 1 for scaling. This increases your activation space exponentially in the number of degrees of freedom you have. So you end up, you're trading off compactness for robustness. So the more robust we want to be, the more equivariance we want, the more compute we have to do. So that's the downside of equivariance. Normally I just say wait 5 years, GPUs will be better. But maybe a very good way to approach this actually is to look for more efficient variants of convolutions. And yeah, I think you can probably combine them. That would be really interesting. That would be a really, really nice project actually, if you could to work on that. It would be super interesting. I think it's cool.
Okay, thank you. Thank you very much again for these 2 wonderful days with lots of questions. You still have outstanding questions also. So yeah, I want to give applause again to you. Thank you very much, Daniel. I really hope that someday we can meet in person, maybe next year or someday in the future. Yeah, thank you everyone for the great questions. Also, yeah, Daniel also need to think hard to answer your questions, I think. So yeah, thank you very much for for today. Yeah, see you guys.
Terima kasih banyak.
Terima kasih banyak.
Very enjoyable time. And if anyone has more questions, I will be happy to answer them. Yeah. Just people can DM me or via the chat on Rocket. I think that'd be great.
Yeah. Of course, participant can still write your own questions in the Rocket chat, and then I will compile it and send it to Daniel later. That's it, I think, for your third lecture. Actually, I want to offer you whether you want to be the moderator, for example, for the meet the speaker with Sakir, for example, if you want. And I think it would be nice, if you can lead the discussion. But we can talk about it later.
Yeah, let's talk about it later. I'll check my calendar. I have some things
course.
organized, but let's.
Of course.
Let's see.
Yeah. Thank you very much.
Okay. Bye.
Bye.
We are channeling the company's artificial intelligence efforts into one recognizable organization, Qualcomm AI Research. Qualcomm invents breakthrough technology that transforms the way the world connects and communicates. Going beyond mobile chipsets, we're inventing AI technology that can be used across a wide range of products and industries, from mobile and automotive to smart homes and cities, ultimately changing the way people live for the better.
Machine learning has already entered every corner of the Qualcomm enterprise. I personally believe that Qualcomm is uniquely positioned to become a key player in on-device AI, which brings with it tremendous opportunities such as increased data privacy for users, reliability of service, high speed and efficient use of bandwidth.
Today, machine learning algorithms such as deep learning use huge amounts of energy to power them. And as AI increasingly moves to low-power edge devices, energy efficiency becomes all the more important.
The challenge we face in the future is about squeezing as much as computation as possible out of every joule of energy. And Qualcomm has a long history of delivering technologies that do just that.
Our mission is to push the envelope of AI and machine learning in the areas that will significantly improve everyday life. We are asking challenging questions, like how do we preserve communication privacy? Can we use deep learning to compress videos? How can we eliminate uncertainty when making life and death decisions? And how can we use this knowledge to optimize Qualcomm chips that run machine learning algorithms?
Qualcomm AI Research is an inspiring environment where researchers collaborate, innovate, and share their findings with the world through high-impact publications. But we do so much more than just writing papers. We actually build AI solutions that are used in billions of devices. In your cell phone, your smartwatch, your drone, your car, and all the other innovative technology of the future.
So if you're interested in pushing the frontiers of artificial intelligence, machine learning or deep learning, and above all, if you feel passionate about the prospect of bringing ideas to life and impacting billions of people, then Qualcomm AI Research is the place for you.
Semua hal berangkat dari sebuah awal. Begitupun kami menjadi pionir. Memutar roda penggerak bangsa dan terus melaju. Kami hadir seperti sebuah keluarga. Dan terus fokus membangun perekonomian negeri. Menjadi yang terdepan, mewujudkan mimpi-mimpi besar. Dari atas awan kami terus bergerak dan berinovasi, melihat negeri ini tumbuh dan berkembang. Inilah kami yang tak akan pernah berhenti mengantarkan Indonesia ke puncak kejayaan. Karena dimanapun dan kapanpun, kami selalu hadir melayani dengan setulus hati.
History, most of the time, is born out of the simplest of acts, just like the birth of our story, starting with the pursuit to close the distance through voice and make exchanging of informations at your own fingertips. And who could have known that was just the first step of our long journey? We had to jump even higher, to open new dimensions of opportunities to explore the world. And we keep on transforming through different times so that we can bring joy and progress for all walks of life. The world is always spinning, just like the sun. Your loyalty in us has always been our light to keep on innovating. No more simple beginnings, further and ahead. We have to keep on running, for you, for Indonesia, with the same vigor that has been driving us from the day one we began. Our 55 years selalu ada untuk Indonesia.